Okay, so we are ready to start chapter 11. So to answer your first question, no, I don't have the test graded yet. I will get them graded over the weekend, so hopefully you'll get them back on Monday, barring any unusual circumstances. I won't promise, but I will say pretty good bet.
If you're going to grade anybody, it's grade mine first.
The one I grade first, I always grade the hardest.
Grade mine fine.
That's fine?
That's fine.
Okay.
Grade mine
Corey?
first. Do you curve the test at all?
Do I curve my test? Curve is a strong word to a statistician, right? So no, I don't curve, but I do sometimes. If the mean is way too low, then I'll shift things as needed to get people where they should have been. And you know, I'll be honest. I had a real feeling based on the review session that we did and the questions I was getting an hour before the test that people weren't ready for it. And I can't imagine why that would be, but today we'll start chapter 11, and a lot of those concepts from chapter 10 will come back around, and they're presented again as if new, so it should catch you back up. So we'll see how the test goes, and then we'll make any decision that we need to there. Let's see, I need my book and notes out of here. This room is not set up well for spreading things out, but chapter 11 is still linear regression, but it is multiple regression. Multivariable. So that's what we mean by multiple regression. The word multiple implies multiple x variables. Right? Technically, people misuse this word all the time, but to a statistician, if you see multivariate instead of multiple, that implies more than one y variable. So multivariate regression or multivariate analysis means you got more than one y variable going on all at the same time, right? There's a lot of applications of that, but we won't deal with that in this class. This is one y variable and multiple x variables. So remember, y is the dependent variable. So it's the response variable. So it makes sense to think that you could have more than one thing that you measure that could explain variability in the y variable. So multiple regression is the study of how those different variables interplay with one another. Right? So a simple regression is 1x, and that model, just review, was yi equal beta 0 plus beta 1 xi plus epsilon I. Right? And that's the population version. How do you know it's the population version? Because it's Greek letters. We would estimate that with b sub 0, b sub 1, and e sub I. Right? Oh, actually, this is not right. There's one thing wrong with this. Anybody notice? This is the stickler on notation.
Is it the y hat?
It's the hat. If I put the error term on there, that means there's no hat, because the observed value is a function of the x plus some random error. When I put the hat on it, now it's predicted value. You don't predict the random error, so there'd be no error term, right? So technically, that hat should not be on there.
So if you leave off the error, then you can put the hat on.
Yeah, go the other way. When you put the hat on, then your best estimate of the error is the mean of the errors. And what's the mean of the errors? Remember those assumptions for linear regression to be valid? What did it say about the residuals have mean? Zero. The residual. So in MA344, you'll learn to call that expected value. But the expected value of the error is 0. Some people will have positive error, some people have negative error. On average, it'll be 0. So when you put the hat on there, you're taking the expectation and the epsilon goes away. So for multiple regression...
You want the pen?
Oh, I thought I did, but... So for multiple... It looks exactly the same, except guess.
Probably has multiple betas.
It's got more betas. That's right. Beta 0 plus beta 1 x1 I plus beta 2 x2 I plus ... And I'm running out of room here, so I'll come down here. Beta p x p I plus epsilon I. So it looks a little bit nasty in terms of notation, but it's really exactly what you're used to. P is, this book uses a P, some books use a K. It's just, that's how many X variables there are. So P equals number of X's. Right? So notice there are P plus 1 parameters to estimate. Okay? So when we fit a multiple regression model, the number of x's in there becomes, remember what we said about degrees of freedom? The sum of squares for model, the degrees of freedom before was a 1 because we had one x variable. Now it'll be p, however many x variables you have. But we'll get to that. Okay, so...
That last one, can I have that back real quick?
What?
That last line.
P plus 1 parameters to estimate. And I guess I could put on here, we will estimate them with B0, B1, ... B sub P.
So the degrees of freedom P or P plus 1?
Well, I'll get to that. It's P, degrees of freedom for model, right? Because the intercept is estimated using the overall grand mean, which is part of the sum of squares total, right? So that's where you lose that degree of freedom down there. But okay. Now, to fit a model like this, obviously you're going to use software, but we do it exactly the same way that we did for simple linear regression. You use the least squares method. And what does least squares method mean? Okay. The least residual, you said least residual error, but what am I minimizing?
You're minimizing the squared residuals?
The sum of the squared residuals, right? So you're minimizing SSE, sum of squared errors, right? Which I know that's what you meant, but I didn't get the sum and the square in there, right? So you're going to do that same thing before. Now, when it's a simple linear regression, we had nice little easy formulas. B1 equal R times SY over SX. Remember that formula? I hope you remember it because you just had it on a test, right? Well, here it becomes much more complicated, right? So the formulas aren't nice. In MA346, which is regression analysis, we'll go into what those formulas are. And it's actually done with matrix algebra. That's why you have to take linear algebra.
Yeah.
Right? So it's matrix algebra gets you those formulas. And so in terms of matrices, they're not too ugly. But if you tried to write it all out like we did before, it'd be difficult. So we won't mess with the formulas for these things in this class. What we'll do is let software run it, tell us what they are. So we're going to focus on the interpretation of these coefficients. Okay? There'll be B's after we have actual data and we get estimates for them. Okay? So the trick is, what do these things represent? When it was simple linear regression, B1 was called the slope, right? Well, it's really the same thing. So this is the slope for the first x variable, and then the slope for the second x variable. But it's a little more complicated because if I fit y on just the first x1, I'll get a slope for that, but it won't be the same slope I'll get when I add another variable. These parameters change in response to each other. Remember, this whole process is to explain the value of yi, to predict yi. All right? So some of these variables might be correlated with each other. So once you've explained some variability in y using x1, maybe x2 doesn't have anything left to explain. Right? So the slope estimate changes. So we'll get to all that. You have a question?
It's kind of like you have two different slopes, but then you're going to turn this one into a vector, and then you're going to take the parallelogram of this and then create a new vector.
Kind of like that, and I like the geometric interpretation that you're giving. You know, vectors, and it's funny. Physicists have trouble with more than 3 dimensions, right? So they call it hyperspace, right? So you have more. Mathematicians and statisticians do it all the time, right? It's like, yeah, so I got 8 variables in my model. I got 9 space here, 8 x variables and 1 y variable. So think of this ellipsoid out in hyperspace, and you're fitting the line. It's not a line anymore. It's a, you know, if you have 2 x variables, you're not fitting a line. You're fitting a plane, right? If you have 3 x variables, now you're fitting a space. Right? So it becomes hard to visualize, but really that's all you're doing. But as you add more variables, the best fitting model, I start to say space or whatever, the best fitting thing will change as the variables interact with each other. Okay? So let's do a quick example here. I need to open a little PowerPoint.
While you load that, is this the chapter where we talk about like heteroscedasticity and multilinearity and all that stuff?
It is, multicollinearity is in this chapter, that's right. Although this book, this is more of like, the idea of this class, applied statistics, is to get a taste of a lot of different things without hitting any one of them in too much detail. So it's in MA346 that you hit multicollinearity a lot. But collinearity, he brought that term up. What that means is you got more than one x variable. If they are collinear, that means they're related to each other. So they are co with the y variable, right? So you have to be careful if you have too much, if too strong of collinearity. Let me make this thing up into slideshow mode. And this is an example that I copied this table out of an actual publication. This was published back in 1984. Factors associated with birth weight and exploration of the roles of prenatal care and length of gestation by these people in the American Journal of Public Health, AJPH. Right? So it was a study of birth weight of babies, and these babies were actually in Orange County, California. Or two California counties, Orange County and whatever the neighboring one, but LA basically. Right? So these are babies born in LA. Right? So what the heck am I looking at here for this table? This is typical output, typical presentation of a multiple regression model. What does it mean, constant? That's the intercept term. What's our symbol for that?
Beta naught.
Okay, beta naught. So let me get a marker. And I'm going to come over here.
And we're going to observe the corner.
And here we go. So we'll write it with mathematical symbols. Y hat I, which is birth weight. So I'm going to put up above that BW, right? Birth weight is equal to, now these values that they're giving, numeric values, means these are B's, not betas, right? But they put a capital B at the top of the table to say these are a lot of times what non-statisticians they'll use different terms for things, but you'll hear them say things like, these are the beta weights. Have you ever heard that? Maybe not. But beta weights, well, they're the beta coefficients, what we call the betas, and the weights, because that's what you weight each of these variables by. It's the rate of change of that variable, or rate of change of the y variable with respect to that variable. So they call it weights. So beta weights. But the intercept term is 2185. Right? So that's not multiplied by anything, it's a constant. And then the next term is sex. And sex is actually a categorical variable, obviously, but they've made it 0, 1, right? So it says in parentheses, male equal 1, right? So you can think of it as plus beta 1 or B1, and that number is 132. 132 times x1, and this is male, and 0 equal no, 1 equal yes. So not today too much, but we'll talk about what we call dummy variables. This is a dummy variable. You've taken a categorical variable and made it into a numeric variable, 0, 1. And regression then works, right? And so on. So then plus, the next one is multiple birth, and it's negative 858. And so x2, and that's multiple birth. What does that mean?
Twins.
Yeah, twins, triplets, quadruplets. If it's a multiple birth, what do you think about the size of the baby?
They're smaller.
They're going to be smaller. So that might be an important predictor of the birth weight of a baby, is if they were a twin, right? And then I'm not going to bother to write all that out, but you get the idea. Plus dot 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 the rest of the model. Okay? So now let's think about it. If I ask you to predict the birth weight of a child that's born in these two counties, and I tell you the values for these different things, you just plug them into the model and get a predicted birth weight. Right? So you start with the intercept. 2185. Now these aren't pounds. They're not elephants, right? So they are grams, actually, I think is what it is. Does it say on here? It does not say, but I think those are grams. So 2185 grams. Yeah.
For black, Hispanic, and other, would that be like, exclusive or one or this or that?
I'm glad you asked that question. It says ethnic group, and then it has 3 variables under that. Black, Hispanic, other. What's missing? What? White. White's missing. Right? So when you use dummy variables to represent categorical variables in a regression model, so what we really have is a categorical variable called race, and it takes on values of white, black, Hispanic, and other. So 4 levels, right? Well, then you make dummy variables out of those 4 levels. They're white, yes or no. They're black, yes or no. They're Hispanic, yes or no. Or they're other, yes or no. But wait, I don't need all 4, because if you tell me, no, they're not black, no, they're not Hispanic, no, they're not other, guess what they are?
They're white.
They're white. Right? So the one that's left out is known as the reference group. Right? So these are then compared to the reference group of white, which becomes part of the intercept. So the reference group is when all of these are 0. Right? So 2185, this number represents the birth weight of a white female, not a twin, and no complications in pregnancy. And then this one's tricky because this is a continuous variable. Length of gestation. The reference group is 0 gestation. Right? So that's the baby is born the moment it was conceived. Right? That doesn't make any sense. But remember, extrapolating back to when all the x variables are 0 doesn't always make sense. But it's just a starting point. Right? So then as they get gestational age goes up, they increase 3.7. Right? 3.7 per what?
Day.
Per day, because this is in days. So per 1 unit change in gestation, they're going to gain 3.7 grams per day after conception. Right? Okay? So now to predict the weight of a baby with a certain set of characteristics, I'm not ready for this yet. I thought I had a slide that gave a particular set of characteristics, but apparently I don't. But so you just start with 2185, and then if they're male, you add 132 grams. What does that tell you about male babies compared to female babies?
That they weigh 100.
That on average, they're 132 grams heavier than female babies, which is a little bit, not a huge amount. Subtract 858 if it's multiple birth. So if that x2 variable is a 1, then you're going to subtract 858. If it's a 0, what happens? Nothing, right? So that's why you make them 0, 1. Right? So subtract 858 if it's a twin or a triplet. Minus 228 if they're black. What does that tell you?
That blacks are born small.
Right. Black babies are 228 grams lighter than white babies on average. Right? Subtract 21 grams if Hispanic. Again, that's white is my reference group. So if they're a Hispanic baby, you're going to take 21 off. Now that's not very much, grams wise, right? So Hispanics and whites are much closer on average than blacks and whites. 133 if they're other. And then minus 257 if there's complications in pregnancy. Does that make sense that it's negative? Subtract 257 grams if there were complications in that pregnancy. That usually means something went wrong, and a lot of times they're born early. Right? Now, length of gestation, we've already talked about that one, is a small number, 3.7. But remember, that's per day. And how long is the normal gestational period? 9 months times 30 days, 270, right? 270 days. So you're going to, if they go full term, you're going to take 3.7 times 270 roughly, and you're adding a lot of grams. Yep.
Is this accurate?
I'm calculating my own weight right now to see how accurate.
The reason why I'm asking is because, okay, with the multiple birth, I could kind of understand that because there's only so much size available within a human frame. So if you have multiple ones, you're going to have to adjust the size accordingly to be able to fit the available allotted space within a human body. But if there's multiple of them, like 2 or 3 or 4, that space is not going to change. The maximum amount of space available isn't just going to expand, which means the 858 might have to go multiplicity of how many multiple births there are.
Oh, I see what your point is. Basically what he's asking is, why is this just if multiple birth? If they're triplets, shouldn't it be an even bigger number? if it's quadruplets. And yeah, you could do that, but guess what the data is going to show? Just think of number of observations of each of those things.
There's a lot of
You're going to get a lot of twins and
triplets.
hardly any triplets, maybe one quadruplet in 2 counties. And so there just isn't enough data to get accurate estimates.
Gotcha.
Right. So basically, they just lump it all together. And say,
And I can kind of see with the blacks, because they tend to be kind of smaller in frame, so the available space
Right.
would be smaller.
but to answer your question, is this accurate? Yeah, this is based on real data that they collected. So part of doing analyses like this is understanding what this all means. You know, what does this mean to say I've got these beta weights or these estimates of the, and what are they telling me? This is what they're telling me. Okay. Now back to this idea of reference group. A reference group was when the gestational age is 0. And since that doesn't make any sense, a lot of times what we'll do, we don't really talk about it in this book much, so you probably won't hear more about it after this. But on the next slide, I have this idea of mean centering the continuous predictor. Right? That makes the reference group be the average gestational period, and then it's 3.7 times the number of days away from the average gestational age, which was 266. We guessed a minute ago at 270. So the average gestational age in this data set was 266. So now notice that it's in parentheses, length of gestation minus 266. I've mean centered that. So if they were born at 260 days, then you've got length of gestation minus 266 is a negative 6. You're going to subtract off 6 times 3.7. If they were born at 270 days, you're going to add 4 times 3.7. Right? So now your reference group is those that went 266 days. Right? So that's more meaningful to your non-statisticians in the audience if you mean center these continuous variables. Okay? Does everybody have a handle on exactly how multiple regression models work? Okay. All right, so let's go back to the notation and the way these things are fit. Basically, if you think about it, when you have that long model with a y value and a whole bunch of x variables, you've got, if you have simple linear regression, so there's only one x variable, you get a set of ordered pairs, right? And you can plot them and make a scatter plot out of it. Well, if you have 2 x variables, you've got 3 space, right? So you have y going up, and then x1 coming out this way, and x2 going this way, and you plot like this cloud of points, an ellipsoid basically, right? And you fit a plane through that. Well, as you add more variables, like I said before, you get ordered triplets, ordered quadruplets, however many x variables you have. So you can no longer conceptualize a scatter plot of the whole thing. I mean, you can kind of envision, this cloud of points out in hyperspace somewhere. But a lot of times the strategy here is, okay, now let's consider each x one at a time. Let's do a scatter plot. How does x1 help predict y? Okay, that looks like this. Now, how does x2 help predict, right? So what you may see produced by software is what we call a matrix, a scatter plot matrix, right? So this is y on the y-axis of all of these plots, and then this one is x1, this one is x2, this one is x3, and so on, right? However many x you have. And then you might see that you got a really strong linear relationship between x1 and y and x2 and y is not so good, and that should be a 3. Or actually, let me make this fancy. You may have one that is a negative relationship, right? So you look at them all one at a time with y. Right? So a lot of times your multiple regression analysis is a step-by-step process and exercise in what we call model building. Which of these variables are important predictors of y? Which can we ignore? So in an analysis, we may end up kicking x2 out of the model and say, well, that one didn't help. Right? So I don't need that one. All right, so the author puts this, and I like this idea. This is really simplifying the heart of the matter. Right? The data that you have can be explained by the fit of the multiple regression model plus things that don't fit, the residual part. Right? So this is random error around the fit of the model. So the idea is to come up with the fit part of it, and then the error, minimize the amount of error. Okay? So the variance of the residuals. Remember this notation from last time? So that's variance of errors is what we call mean squared error. Right? And that is the sum, I equal 1 to n, of e sub I squared. That's the sum of squared errors. And then you divide by its degrees of freedom. Now let's think about degrees of freedom for a minute. Remember our old friend, the ANOVA table? Now the ANOVA table is going to have the model, right, or the regression line with degrees of freedom of p. The total degrees of freedom is always n minus 1, and they have to add. So if you have p for the model, and you have n minus 1 for the total, what would error degrees of freedom be? So I need to label here. What'd you say? You can get it by subtraction, right? So it's n minus 1 minus p, which is, just scratch paper here, n minus p minus 1, which is fine. The book then factors out the negative and says minus p plus 1. Right? Now why do you suppose they like that? Well, what is p plus 1? I had it on there earlier. The number of, the total number is not number of x's, but number of coefficients, the number of betas that have to be estimated, right? So p plus 1 is number of parameters to estimate. There's p of them that are coefficients of the x variables, because there's p x variables. Then there's the beta 0 we also have to estimate. So this is the intercept plus p more, p plus 1. So the error is always the sample size minus the number of parameters. In a simple linear regression, remember it was n minus 2? How many parameters did we have? Beta 1, beta 0, beta 1. So we had 2 parameters, n minus 2. Right? So it's just n minus quantity p plus 1. You don't really have to remember that because you can get it from subtraction. If you know what your model is and know what your total is, you can always get it from subtraction. But okay, well, I've got just about enough time to... That thing lost me again. I want to do an example using Excel. All right, so we're going to do a little bit of Excel today, and then on Monday we'll see how to make SAS do these models. Multiple regression analyses are not for your calculator. All right, calculator doesn't. Well, some of them, like the Inspire, might, but let's go to. I'm going to load or open a spreadsheet here where I've already run the analysis, but I'll set the stage here. Let me zoom this up just a little bit. What this is data from an example in chapter 11 in the book on college GPA. So that's this column B. Right? Column A is just observation number. And then this is high school math score, and it's been scaled to a scale of 1 to 10. Right? So basically, how good did they do in math in high school? How good did they do in social studies and in English? Or no, science. HSS is science. So high school science, high school English. And then SAT on the math part, SAT on the reading part, and on the writing part. Right? And then a variable for gender. Now this particular variable gender, I'm not going to do anything with it today, but notice it has 1s and 2s in it. That's fine, but it's not near as nice for interpretation as 0, 1. Right? But, you know, it's okay. Because what the model is going to do is say, well, what's the rate of change of GPA per 1 unit change in the sex variable? Well, when you go from 1 to a 2, that's a 1 unit change, so it works. And you'll get exactly the same parameter estimate, but you'll get a different intercept. Because now the intercept is for a sex of 0, which doesn't even exist, so it's harder to interpret. Right? So first thing I would do if I was analyzing this data is I would change that by subtracting 1 to get 0s and 1s. But, so I've created a regression table here. Let me talk through the results just in case I run out of time, and then I'll show how you do that. Right? It's actually pretty easy since you already know how to do a simple linear regression. All right, so this part of the table is the ANOVA part. So let's dissect that. It's got regression, SAS will call it model, same thing, with 6 degrees of freedom. So where's the 6 come from?
The 6 variables.
It's got 6 variables, and they're listed down here. High school math, high school science, high school English, and then the 3 SAT parts. Okay, so 6 total. So you get 6 degrees of freedom. Where's the 149 for total come from?
Subtraction.
Well, okay, yeah, you both are kind of saying it's by subtraction, I'll bet. But 149, how many observations are in this data set?
150.
150, because that number is always n minus 1. Right? So you can look at that, add 1 to it, and you know what your sample size was. Or you can scroll down this thing, and at the bottom you'll see that the observation number of the last one is 150. Right? So there's 150 observations. And then you get this residual degrees of freedom, or error degrees of freedom by subtraction, but it's also 150 minus 6 plus 1. So 150 minus 7. Right? So 143 degrees of freedom. So sum of squares due to regression, sum of squares due to error, and sum of squares total. It all works just like it did for simple linear regression. The thing that is different is the interpretation of this F statistic. So let's talk about that for a second. The F statistic is the same as it was before, mean square for model over mean square for error. Right? And it has, that little squiggle means is distributed as an F distribution with degrees of freedom in the numerator. How many degrees of freedom are in the numerator? 6 this time, right? In general, it's P. So I'm going to write P. So P degrees of freedom in the numerator, and then how many in the denominator? It was 143 for this one. 149 was total. This is the degrees of freedom for error. So in general, it's N minus P plus 1. Right? So this notation, I'm not sure if he writes it this way in the book, but that little squiggle, officially called a tilde, means is distributed as an F distribution with P degrees of freedom in the numerator and N minus quantity. Okay. So now, what is the null hypothesis for this F? Right? I mean, it's a test statistic, and it has a p-value. If you go back here, there's a p-value out there. It's highly significant. 2.69 e to the minus 8. Right? So that's 0.00070. So very small p-value. What is the null hypothesis for that? Well, when it was simple linear regression, it was beta 1 equal 0. Right? The slope is equal to 0. When it's a multiple regression, this is called the overall F test. Basically, in words, it's the null hypothesis is this model does not help predict Y. Right? So, model does not predict Y. In symbols, what would that mean for each of those x variable coefficients, the slopes on all those x variables? They're all equal to 0. So it's beta 1 is 0 and beta 2 is 0. So they're all equal to each other because they're all equal to 0. All right? So beta 1 equals beta 2 equals beta 3 dot 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 equals beta p equals 0. Now how do I write the alternative for that? A not equal everywhere. So they're all not 0. Remember, the alternative is the complement to this event. This says, oh, there you go. This says they're all 0. What's the complement to that? They're not all 0, which means, what did you say, Laura? At least one is not 0. Right? So it's hard to write that out, but I always say this: at least 1 beta sub j not equal 0. And then if you want to get really precise, you say j equal 1 dot 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 to p. And that's not a very good j. I did it again, but right? So at least 1 beta j is not 0. So at least one of these variables does help predict y. It's not saying they're all strong predictors. It's saying at least one of them is a strong predictor of y, or a significant predictor of y. Okay? All right, that's a good stopping point for today. 1 minute early. Just remember that. So we will see you on Monday. You will not have any homework due on Monday because we haven't done enough to really get you going yet. But